Okay, we're shake table number 1. I'm Kate.
I'm Jack.
I'm Caden.
I'm Tony. I'm Tomas.
So our problem statement was we need to design a compact portable shake table that can safely test student projects simulating an earthquake motion. The system should minimize external cords and wiring for easy setup and storage. It must be reliable, cost-effective, and capable of adjustable vibration settings to accommodate different testing needs. So our professor needs a shake table. It needs to be safe to use. It needs to simulate an earthquake. It should minimize cords, and it must be smaller than the previous shake table that she had. So the requirements, it shall be 2 feet by 2 feet, shall shake in a constant pattern, shall last at least 2 years, shall have a stop switch and a drill, and shall be easy to use, and shall cost less than $100.
Alright, so these are just some rough drafts, like drawings of our different ideas. We got 1, 2, and 3 over here. Main difference between them all is how they'll move. So for the first one, it's a smaller design. It utilizes a platform with 4 pegs with springs attached to the main shake surface. The motor is directly underneath the shake platform, and it will rotate in a circle attached to the platform, just kind of rotating in a circular motion. It'll use the springs on either side just to help the shake table, just for stability, and also just so that it takes the load off of the singular pole holding up the shake table. Design number 2 is very similar to design number 1. The main difference is the placement of the motor and the way that it moves. So the motor is also underneath, but then there are these railings on either side, since the shake table will move horizontally rather than in a circular motion. And the motor, it'll rotate, so it spins this little disc thing, and then that will move a pole. No idea how that's going to work yet, but we'll figure that out. And it'll shake the table side to side along the guide railings, helping it for a more smoother, just better shake. Design 3 is a bit different. Still using the springs on all 4 corners or rubber bands. There and there, holding up the shake table. And then the only difference is it'll have the motor off to the side, similar to what she has right now, where it's a drill on the side, except this will be a motor. And then it'll shake horizontally, just as number 2 did. It does make the table a little bit larger, which we probably won't do, but just makes the table a bit bigger. It does allow it to be easily fixed, since it's not all compacted right underneath the table. You can just easily replace the motor if you need to. And then it just the same way it'll rotate the disc, and then there'll be a metal beam attached to it, which will move the shake table in a way.
Alright, so our Q matrix, obviously we've got our 3 designs so far: the circular shake pattern, the 2 horizontals, one with the motor to the side, one with the motor underneath. Then we have our criteria for those. Obviously the most important being size and durability, as given by our stakeholder. Those are emphasized to us. And then going through the future, we can see that the horizontal shake with the motor underneath is what won, or is what got the most points, as this kind of combines the best way to have a small, compact shake table, but also still being pretty durable, pretty easy to access, pretty easy to use. Yeah, so obviously the best design there was the horizontal movement with our motor underneath. This combines, it keeps it in a very small, compact size, but you still maximize the durability of it. Because it's a simpler movement pattern, so there's less things that can go wrong. And yeah, obviously outscored other designs and it won by the highest, by a large margin.
And then we categorized our risks with this design into two areas. The first being failure of components, and that would be motor fastenings coming loose if the shaking was too much for the fastenings. The wood strength, if it was too thin, it might crack. And then power and motor failure. If the motor were to overheat or keep malfunctioning, that obviously wouldn't be good. And then with those previously stated, cracking or an overheating motor might cause safety hazards. And then the other area would be inaccurate simulation, and that would be the wood material bending or project sliding off the table while it shakes. And then again, we need a reliable motor that will consistently shake the projects and yeah, just overall be consistent. And then for movement allowance, if the springs allow too much movement, the table might break, and if they don't allow enough, the table wouldn't shake.
So we came up with our first prototype. This is what it is. It's the first prototype. It's quick and dirty. But as you can see, it's got 4 posts, one on each quarter with springs holding the shake platform right here. Underneath, you can kind of see it. I don't know if you can see it or not, but there's 2 rails underneath that let the shake part slide back and forth when the motor shakes it. You can't see a motor underneath, obviously, we didn't put a motor under there, or the control system, which would be mounted on one of the 4 corners or on the bottom, such as right here, to turn the table off, on, adjust different settings, such as intensity. And we, during the brainstorming process, we also thought we might put in a vibration control system, such as rubber feet on the bottom, just to keep the table from moving around too much while it's shaking. Prototype testing, we haven't tested it yet, but there's 3 main areas that we want to test. Obviously, is it compact? We can test it, take it to our closet, to the shelf, make sure it fits there. Second, can it break a structure? We can build something small, something pretty easy to break since it's not too durable right now. Put it on there, take a hand underneath or something, shake it around, see if it'll break it. And the last one, is it durable enough? We can, just based on the design, we can shake that table pretty hard and see if it breaks. Put a heavy load on it, see if the springs fail, something like that. Our milestone dates, we got 4 main milestone dates. November 10th, we want prototype 1 to be complete and tested and get feedback on that. So by November 24th, we can finish testing and completing prototype number 2. And then at December 8th, we want the whole shake table to be assembled and completed, as well as tested and tweaked. So we have a good time buffer before December 15th, which is our project handoff date. This is our Gantt chart. I'm not going to bore you by reading the whole thing, but some of our main milestones, again, prototype number 1 complete, prototype number 2, shake table completed, testing and changes completed, and then the final project handover again at December 15th. That's it.